You know that feeling, right? That little spark of chaos when you're talking to an AI. You ask it the exact same question twice, and you get two totally different answers. It really feels like there's a ghost in the machine just messing with you. Well, today, we're going to hunt down that ghost and figure out exactly what's going on.
All right, let's get right into it. The whole mystery really boils down to this one question. Why do large language models give us different answers even when we've specifically told them not to be creative? I mean, we all see it happen, but when you stop and think about it, that's a really strange bug for a computer to have.
And just to show you this in action, check this out. Researchers prompted a model 1,000 times with the same simple request about Richard Feynman. Now, for the first 102 words, every single response was identical. But then, a split. Some of the answers said Queens, New York, while others said New York City. It's such a tiny difference, but that one little change completely alters everything that comes after it. And that right there is what we're calling the LLM reproducibility puzzle. We're going to break down why this happens, why the explanation you've probably heard is actually wrong, and then unmask the real culprit.
So to really get the puzzle, you have to know about this one setting called temperature zero. Think of it as the no creativity switch. When you turn it on, you're forcing the model to always pick the single most likely next word. In theory, this should make the output 100% predictable. It should be the same every single time. And yet, it's not.
So, what is going on? Well, like any good mystery, this one has a usual suspect. And in the world of computer science, there's a super popular theory that everyone loves to point to whenever these weird random results pop up.
It's called the concurrency plus floating point hypothesis. It sounds technical, but the idea is actually pretty simple. Modern GPUs are doing billions of calculations all at once, in parallel. And since you can't predict which calculation is going to finish first, the order of the math changes slightly every time, and that leads to different results. Seems like a pretty solid theory, right?
This whole theory hinges on this really deep fundamental quirk in how computers do math. It's called floating point non-associativity. Basically, because computers can only store so many decimal places, the order you add and subtract numbers in really matters. That simple rule we all learned in school that a plus b plus c is the same as a plus b plus c, yeah? For computers, that's just not true.
And this example is just mind-bending. Look at the first line. You add a tiny number to a gigantic one, and the computer basically loses the tiny number in the rounding. The result is 0. But in the second line, you subtract the two huge numbers first, which cancel out, leaving just the tiny number. Same numbers, same operations, totally different answers. It's wild.
Okay, so that has to be it, right? The random race between the computer's cores mixed with this bizarre math, that's our ghost. Case closed. Well, not so fast.
And here comes the plot twist. Our usual suspect? It has an alibi. When researchers took a core LLM operation, like a big matrix multiplication, and ran it over and over on a GPU, they got the exact same, bit-for-bit identical result every single time. Now, if that random race between threads was the real problem, this should be impossible. So something else must be causing the randomness. So, if it's not the random timing of the cores, then what is the true culprit? Well, the answer is something way sneakier. And it all has to do with how AI models handle lots of requests at the same time. It's a little thing called batching. Now, to unmask this culprit, we need to talk about something called batch invariance. An operation is batch invariant if the answer you get for your query doesn't change no matter how many other people are using the service at the exact same moment. I mean, logically, other users shouldn't affect your answer at all, right? Think of it like a delivery van. Your request to the AI is one package. If it's the only delivery of the day, the van takes a simple direct route to you. But if your package is in a full truck, a big batch of requests, the driver is going to optimize the route for the entire group. Your package still gets to the same place, that the path it takes, the order of operations, totally changes. The group affects the individual.
And here it is, the smoking gun. This code runs the exact same calculation twice. First, all by itself, and second, as just one part of a larger batch. And look at that difference. It's not some tiny little rounding error. It is a massive numerical gap. The math literally changes depending on who else is in the queue.
And that connects all the dots. The randomness we're seeing isn't from the GPU's cores, it's from all the other people using the AI. The server load is totally unpredictable. That unpredictable load changes the batch size for your query from one moment to the next. And as we just saw, a different batch size changes the math, which ultimately changes the final words you see on your screen. The ghost in the machine was just the crowd. So now that we've finally unmasked the true culprit, what can we actually do about it? How do we solve this case and finally get the true, predictable results we're looking for? Let's take a look at the path to determinism. The researchers who figured all this out came up with a really elegant three-step fix. First, they went in and found the 3 specific operations that were causing all the trouble. Then, they completely re-engineered them to force a consistent calculation method, no matter how big or small the batch size was. And the result? The math for your request now stays identical, whether you're the only one online or one of 1,000. Now, this was a ton of really complex work. So the big question is, did it actually fix the problem? Well, they took that same Feynman prompt from the beginning and ran it another 1,000 times with their new deterministic system. And the results are just stunning. Before the fix, running that same prompt 1,000 times got them 80 different unique answers. After the fix, 1,000 prompts gave them exactly one answer. Every single time. The ghost has officially been captured. But okay, what's the catch? Is it crazy slow now? Well, there is a performance cost. The deterministic version took 42 seconds to run the 1,000 requests, compared to 26 for the normal one. So yeah, it's a noticeable slowdown, but it's not a deal breaker. This fix is actually practical. So why does any of this matter? I mean, this isn't just about getting neat and tidy repeatable outputs. This breakthrough actually enables something incredibly important for the future of AI, true on-policy reinforcement learning. And that's a super powerful way to train AIs, but it requires perfect, and I mean perfect, consistency. And this number right here is the ultimate proof that they succeeded. KL divergence is just a mathematical way of measuring how different two things are. Before, there was always this small chaotic gap between how an AI was trained and how it actually performed. With this fix, that difference is now 0. It's a perfect alignment. For AI researchers, this is a huge step forward.
And all of this leaves us with one final thought. We started this whole journey just hunting down a small, weird bug. But the solution led to a completely new level of precision and control over these massive AI systems. So the real question now is, when we can demand this level of predictability from our machines, what entirely new possibilities does that open up for all of us?